Okay, hello. So yeah, I will talk about generalized information diagrams and interpreting a weak version of the second law of thermodynamics. And this is joint work with Pierre Baudot, Rick Quax, and Patrick Fourier. So yeah, maybe I'll stand here. Okay. So the one slide summary and also the outline for the talk is that whenever you have a chain rule, and you might imagine the chain rule of entropy that we saw before, or there is also chain rule, for example, for Coolback divergence, which we just saw in the last talk. So the claim is whenever you have a chain rule, then you get information diagrams. And these information diagrams, they look like this. So yeah, at the top, for example, you get the conditional entropy, conditional neutral information, interaction information. And at the top, bottom one, we have a more abstract information diagram for a more abstract case. And what I also want to argue that it's kind of worth exploring what that means. And in particular, I will explain the second law of thermodynamics, or a weak version of that. Okay, and this is also the outline of the talk. So first I'll talk about chain rules and what they are. So if X and Y are discrete random variables, then we can talk about the Shannon entropy. And for example, only about the Shannon entropy of the random variable X. But we could also look at the joint entropy of X and Y. And we can look at the conditional entropy. So that's kind of the information that is left in Y on average once we know the evaluation of X. And they're related by the chain rule. So the entropy of X and Y together, the uncertainty, equals the uncertainty in X plus the uncertainty that's left in Y once we know X. And similarly, we have a chain rule for Coolback-Leibler divergence. So here, here again, X and Y are discrete random variables. But now we do not only have one probability distribution that assigns probabilities to joint evaluations, but we actually have two, P and Q. And then we can look at the KL divergence between those two distributions, for example, only on X. So then we're comparing the marginal distributions, basically. Or we can look at the joint KL divergence. And by the way, I have to say kind of KL divergence is synonymous with relative entropy. I think that term was used more often in the last talk. So we can use also or look at the joint KL divergence. And we can also look at conditional KL divergence, which basically says, on average, if we see kind of the evaluation of X, how much do P and Q differ in Y? And then again, we have a chain rule. So the difference of P and Q on the whole joint of the random variables equals the difference only on X, plus the difference that's left in Y once we already know X. And there are more examples of chain rules. So for example, the Thales alpha entropy, the alpha KL divergence, cross entropy, the feature advantage in machine learning, and also Scheitin's Kolmogorov complexity also satisfies a chain rule. Okay, and now the claim is that whenever you have such a chain rule and satisfy certain technical conditions, then you actually get information diagrams. And first I want to explain that on the example of entropy, but basically all the examples that I just showed run through the same reasoning. Okay, so why does the chain rule of entropy give us information diagrams? So if we look at the chain rule, then we see that this looks pretty similar to an equation of sets. So basically we can just make some symbol replacement. So we can remove the H that stands for entropy. We can replace the comma by a union, and we can replace the plus by a disjoint union, and we replace the vertical bar for conditioning by a set minus. And then we get that equation, and that equation is trivially correct for sets. And we can, for example, also visualize that with Venn diagrams. And if instead of kind of visualizing it for sets, but we kind of keep the original notation, then what we get is called an information diagram. So that is kind of the whole idea. But then Hu Kuo-ting in 1962 had the idea that this can be generalized to an arbitrary number of random variables, and also for like higher order information terms. So what one can define is mutual information. And mutual information is the information that Y carries about X. And if you look at the right-hand side and kind of try to think of an analogous term for sets, then you get X set minus X set minus Y. That's kind of the idea. And that is actually just the intersection of X and Y. So it seems like mutual information is something like an intersection. And similarly, you can define interaction information. And there you just use the same formula, but for a higher degree. And usually you probably know this for 3 random variables, but you can really do it for an arbitrary number. And again, this interaction information of Q random variables is basically nothing but the intersection of Q sets. And the conclusion of Hu was that if you have any additive formula of these functions of entropy, interaction information, and so on, and you want to check whether this additive formula is true, then you just need to do the following. You just remove all the I and H symbols from the equation you want to prove, and you replace some symbols. So the semicolon becomes an intersection, the comma becomes a union, the vertical bar for conditioning becomes the set minus, and the plus becomes the disjoint union. And once you have done all these replacements, you're left with a set equality. And then you just check, is the set equality that you end up with, is that a true equality? And if it is, then the original formula is also correct as an information equality. And this can be formulated by saying that you basically have a signed measure from the sets to the information functions. Okay, now I want to look at like a short example of kind of illustrating this method. So we have this equality and we want to check, is this equality true? And basically we don't really know by just looking at it, and it would be complicated to kind of expand all the terms. But if we do all the replacements, we replace I with nothing and H with nothing, and the comma with a union, and the semicolon with an intersection, the plus with a disjoint union, and the vertical bar with a set minus, then we end up with this set equality. Okay, and maybe we're still wondering, is this set equality, is it true or not? But now we just draw the Venn diagrams, because we just have 3 sets here. It shouldn't be too difficult. And what we see is that kind of the green part is just this green shape. The red part is that red shape. And the golden part is this golden part. And we immediately see that the equality is correct, because this disjoint union of those 2 parts is actually the golden part. So that means we have proven by using Hu's theorem that the original information equality is correct. And then usually you would immediately draw this sort of information diagram and figure it out there, because you just know that information functions behave like sets. Okay, and what we did was to generalize this result. So we kind of wondered, what is it actually about entropy that makes these information diagrams work? And the idea is that probably not so much, and probably we can kind of abstract away from it a lot. And so the goal was to find some abstract formulation that captures all the examples that I showed before. And what we found was that we can do the following. So we replace the collection of random variables together with the joint operation with any commutative idempotent monoid. We replace the information functionals with any abelian group. the conditioning operation actually becomes any additive monoid action. And the entropy can be replaced with any function from the monoid to the group that satisfies the chain rule. And then the chain rule looks like this. And as you see, so here you kind of have the joint, it's just a product in some monoid. And here you have this dot. So instead of saying we have a vertical bar and then the x, we formulate it with this dot. And the reason is just that monoid actions are in the mathematical literature formulated with a dot. And this notation actually is better suited to do some of the derivations. And so in this general framework, one can then like show that, that information diagrams actually pop out. And the result is that we obtain information diagrams for entropy, Coolback-Leibler divergence, alpha entropy, alpha KL divergence, cross entropy, the feature advantage in machine learning, and also Kolmogorov complexity. Okay, and finally, the last part that I want to convince you that it might be worth to explore what this means. And there I want to first look at the example of Markov chains and what the information diagrams then look like. So imagine you have n random variables x1 until xn, and they are called a Markov chain if the probability of xi does only depend on the last time step. And equivalently, you can say that the entropy of xi also only looks at the last time step. And now we want to like think about how can we visualize this with information diagrams, and this was like already done by Raimund Jong, I think in 1991. So the first case one can look at is n equals 3. There the formula looks like this. So intuitively, x1 does not carry any information about x3 once x2 is already known. And we can kind of reformulate that intuition by saying that the mutual information of x1 and x3 conditioned on x2 is 0. And if we look at the corresponding information diagram, then remember that this conditional mutual information, that kind of the semicolon is an intersection and the vertical bar is a set minus. So what we end up is actually this region. So the intersection of x1 and x3 set minus x2. But we're saying that this region is 0. So we can kind of take the circle and move it down until this region just disappears because we don't need it if we already know it's 0. And if we do that, then the information diagram looks like this. So it's almost like an opening fan. So you're kind of taking 3 circles and open them up. And if you have more random variables, which you can do because like information diagrams work with arbitrary numbers of random variables, they're just like more and more difficult to visualize usually. But for Markov chains, it's pretty easy, and it's kind of the same picture. So no matter how many random variables you have, you just get this opening picture of an opening fan. Now I want to explain to you how one can use these information diagrams to model the second law of thermodynamics. But I have to say, like, I'm not a physicist, and the description of the second law of thermodynamics is weak and also relatively abstract. So I hope I don't disappoint anyone. Okay, but we start with a probability P of x1, which is the macro state of the universe at some time point 1. So it's a probability distribution over microstates. And we take some transition matrix, which is basically supposed to model how microstates evolve over time through the physical laws. And we assume everything is discrete. So P of x1 is discrete in the transition matrix as well. And then we can take the joint of all of this and then marginalize to get the macro state of the universe at some time point I. And this is a Markov chain. And the reason it's a Markov chain is just because in this product, at each time step, you just look at one time step before. And then you can actually show that from this, it follows that you get a Markov chain. And additionally, we assume that the transition matrix is doubly stochastic, which means that we could also kind of go back in time and again would get a probability distribution. And this is a technical condition that's important later. And then the weak version of the second law of thermodynamics basically says that the entropy of P in time step I, it cannot decrease at any point in time. So if you let I become larger, then the entropy cannot get smaller. A stronger version would say that kind of the distribution would approach the uniform distribution, but that's not what I'm saying here. And the question is, how can this weak version of the second law be proven with KL diagrams? Okay, that's the question. And there's a trick. So we can take the uniform distribution, Q of x1, build the joint, marginalize out, and then this marginalization, so the distribution that gets propagated, is again uniform at time step I. And the reason is that we have this double stochasticity as a property. And then the trick is to look at the Coolback-Leibler divergence between P and Q at time step I. And because Q is uniform, in this formula, Q of xi is some constant c, because the uniform distribution gives everything the same probability. So overall, we get the constant minus the entropy of P at time step I. So essentially, the divergence is just the negative of the entropy. So to show that the entropy cannot decrease, we need to show that the Coolback-Leibler divergence cannot increase. And how can we see that the Coolback-Leibler divergence cannot increase? And basically, I'll argue that we can see this visually, in a sense, and with some thought in these Coolback-Leibler diagrams. So the red circle here is supposed to be the Coolback-Leibler divergence between P and Q at time step 1. And the golden circle is, for example, the Coolback-Leibler divergence at time step 4. And they're arranged in this like fan-like structure again, because we have a Markov chain. So it's kind of again valid. And now the question is, why is the divergence at time step 4, for example, why is it smaller than at time step 1? And in order to show this, we basically need to argue that the divergence at time step 4 is contained in that in time step 1. So we want to show that this whole circle is in reality actually inside the one for time step 1. And for that, we look at like at any region outside of the red circle, for example, at this part, and wonder, like, why does this part disappear? Why is it 0? And the argument is relatively intuitive. So this part, for example, this cell, is basically the intersection of the violet part and the golden part, but then set minus the red part. Because we're outside of the red part, we kind of take set minus. But taking set minus in kind of, yeah, this whose theorem framework means that we actually condition on the first time step. But if we condition on the first time step, then P and Q are the same distributions. And the reason is that P and Q both evolve using the physical laws, using the same transition matrix. And since they're using the same transition matrix, the whole distributions are the same after conditioning on x1. And if they're the same distributions, then their Coolback-Leibler divergence just disappears. And so the result is that this whole cell is just 0. And that can be argued for any of the cells. So all of them just disappear. And this is the picture. Yeah, and that's basically it. So the Coolback-Leibler divergence gets smaller and smaller. It might also stay the same. So it could also be that maybe this region is also 0. Then this part and that part would be the same. So we're, like, with this argument, not proving the strong version of the second law of thermodynamics, which actually in this case doesn't even hold, but one needs more assumptions. But we at least get this weak version. So the summary of the talk is that I argued that whenever you have a chain rule, you get information diagrams. And I think it's worth exploring what this means. Okay.
Thank you. Someone in the back, I think. Yeah.
I have a question, and I'm not totally familiar with this area, so if it doesn't make any sense, just let me know. But I'm curious if this still works if the incremental steps between time 1 and time 2 are not discrete, but rather continuous.
I don't know. Yeah, so it depends a little bit. So you want to kind of make the time steps continuous, but are your random variables still discrete or not?
Random, I guess my question is the random variables can be discrete, but the time steps themselves being continuous.
Yeah, I think so. Okay, so here someone says it does not work.
It doesn't work because according to Aristotle, time is discrete and only space is continuous.
So I was asking the other question.
Okay, so that was the philosophical answer.
Yeah.
So I think probably further research would be needed. So the thing is that once you kind of have a continuous situation and you, for example, build the joint distribution, then even if like at every time step you are discrete, overall you're not discrete anymore. And if you're not discrete anymore, then you run into problems. So for example, I need in my theory a commutative idempotent monoid. But if you, for example, take the differential entropy of some random variable joined with itself, then this can be minus infinity, even if the entropy of the random variable is not minus infinity. So and like if you would be idempotent, then this is not allowed. You would need to get the same result. And like maybe there are some ways to fix this, maybe by like using another reference measure, not the measure that you would usually have like in the product space. But I'm not yet sure if that works. Yeah.
That you had a question?
Yeah, I wonder. I mean, for the previous question, where you were asking if time is continuous, so you take the limit. You could take the limit as time steps get very small. Each time step is still a Markov stochastic process. So then you would still get this version of the second law for that. For
yeah, okay. If we do just for very. Yeah. Okay. Yeah.
So my question is, I wonder if you can prove the data processing inequality for this. Data processing says if I have two probability distributions P and Q, and I substitute them to the same stochastic process, which doesn't have to be doubly stochastic, just any stochastic process, then the relative entropy between them decreases.
Yeah,
it's not increasing. I mean, it actually looked kind of like you were doing that here. So
yeah, so kind of your statement here is that like those two together are larger than this usually.
Right, but you were focusing on doubly stochastic processes, and data processing is stronger, right? It holds for any stochastic process, even non-entropy increasing ones.
Yeah. So
yeah, need the double stochastic property.
Yeah, I was confused as to whether this was you were actually reproving the data processing inequality for double stochastic processes, or actually my question is, since data processing is not that easy to prove, that maybe if you could prove it using this language, that would be great.
Yeah, so I think kind of one problem is that if we take the Coolback-Leibler divergence, which is actually what I used for these information diagrams, then we do not have then the data processing inequality does not hold anymore. And the reason is that some of these regions can actually generally be negative.
I'm confused. What I was saying, relative entropy and Coolback-Leibler divergence, I meant the same thing.
They are not the same thing. Sorry?
They are the same thing.
Yes, they are.
Right.
Yeah.
So data processing says for Coolback library divergence between P and Q, if P gets mapped to P prime and Q gets mapped to Q prime by the same Markovian stochastic process, then the Coolback library divergence decreases or is non-increasing for any stochastic process, not only double stochastic.
Yeah.
We need to take this.
Right. No, it's a good, yeah, it's probably a good question. I was thinking kind of about the mutual information and not about the divergence, and then kind of about the generalization of that, but we can, yeah.
Okay, you guys have something to talk about. So let's thank all the speakers of this session again.